Welcome everyone to the first episode of our podcast, Beyond the Threshold, a podcast about digital PCR, where me and my colleague Jan, who's a senior technical expert for digital PCR, will answer your questions, talk about interesting things that we come across, and it's all about digital PCR.
Yeah, and I'm happy here to co-host with Jonathan, who's an associated principal investigator at QIAGEN in Hilden. And for the first episode, we are going to answer a couple of questions that came in during our live roundtable session in December. And then starting with the next episode, we're going to focus more on specific topics. So we'll start out with the first and the very basic one. Jonathan, what's the D in digital PCR or dPCR stand for?
Well, there's a short answer and there's a long answer. The short answer is the D stands for digital, which is obvious. But the question, of course, is where comes the term digital from? It actually comes from a paper in 1999 published by Bert Vogelstein and Ken Kinsler, which was kind of a review paper where they talked about this type of PCR. And there they termed this digital because your partitions are either positive for your target of interest or they are not. So it's ones and zeros, hence the digital. One could have also termed it like binary PCR, or what are you always saying, Jan? How one could have named it?
Binary, or you could call it on-off. But then the binary, I think, has the drawback that you might interpret it as just having a yes/no answer, which it doesn't. It has a quantification, which binary usually, I mean, it depends how you read it, but it's a lot of ones and zeros, but they add up to a total number, which is why I think they called it digital. And I think the name just stuck, basically.
Yeah, well, it was because the first overall review paper talking about this and bringing the concept to the forefront. So digital because partition is positive or negative, ones and zeros. But actually, the idea of digital PCR is much older than 1999. And in fact, there are some review papers out there already from the late 80s speculating about doing this kind of PCR and using Poisson statistics to calculate the copy numbers. Already in the early 90s and mid 90s, there were methods using, it's called limited dilution PCR that was used. That was kind of the same as digital PCR. So the ideas and concepts are much older than that.
Yeah, and the second question we got is about amplitude multiplexing, which is one way to look at multiple targets at once in the same channel. And the question was, how does it really work if I have two assays running and I have a partition where I have both of my targets in the same partition, so assay A and assay B? Do they normally just add up the number of the intensity? So does the signal add up? And do I expect to have double that? So what's your experience with that if you amplitude multiplex?
Well, they just can add up if both PCR efficiencies are not inhibited by each other, having two templates in the same partition. But usually there is some form of interaction and there's some form of competition. So the partitions that contain both targets will not add up perfectly. However, that's not really a problem. You only have to make sure that the third band, where both templates are in there, is high enough that you can separate each positive cluster fairly nicely via the relative resonance of the partition. Besides that, it doesn't matter.
Yeah, I've also recently tried my hand on a couple of amplitude PCRs, and what people also generally don't think about is the background that you have. So I've had a couple of examples where the background was at, let's say, 20 fluorescent units, and then A ran at 30, B ran at 40, which then you would say, oh, 30 plus 40 means the double ones should be 70. But they're really not, because you also have to factor in the background. One is 10 above the background, the other one is 20 above the background. So if you add them up, it's 30 above the background. So they end up at round about 50 instead of 70.
All right, so the next question. What makes a robust assay, and what affects the background fluorescence of a probe?
So that is a bit of a loaded question, I would say, because it also depends on what do you define yourself as a robust assay. I think that kind of depends on the person working with it. There are some people who say, well, my assay has to be basically perfect from a very low input amount of target DNA up to very high. And it also needs to work if I reduce the annealing temperature by 5 degrees, it still needs to look the same because I need to make sure that I never get any quality issues. There's other people who say, well, you know, if I run it at 60 degrees, it looks kind of okay. And it has an R-square value of 9 something, not 9.9, but 0.91 or whatever. And then that's still robust. So it depends on the definition. From my side, my personal opinion, generally, assay is robust if you can multiplex it with other assays without getting big dips in the performance. Performance dips in dPCR, unlike for qPCR, are usually visible by just the signal going up or the signal going down. And I would say a robust assay is an assay where if you change the temperature by maybe 1 or 2 degrees, it still looks kind of okay. And if you multiplex it, it also remains looking fine. I've seen quite a number of robust assays, but I've also seen some assays where if you alter the annealing temperature by 1 degree, you basically lose all of your signal and nothing works anymore. I have yet to find any convincing chemical explanation as to why that is. To be honest, I just think some primers and some probes behave weird, and that is what you have to live with if you work with PCR.
What are your thoughts on sample cleanliness or sample quality? Do you think, I mean, for me, a robust assay also must perform on like roughly 90% of the samples you throw at it?
Yeah, but that also depends on what you're looking at. I mean, if you're working in an environment where you're, for example, producing a virus for clinical use in the end, you're normally working with stuff that is reasonably clean, because at some point you might want to put it in a person or in an animal or whatever, so it has to be clean. If you have somebody who's working with stool samples, that by definition most people would say probably not that clean. So it kind of depends what you really need to measure, and the assay needs to fit the purpose. So if I work with stool samples, yes, I probably need an assay that is relatively unaffected by PCR inhibitors that are floating around in my samples. Same with wastewater or with any environmental DNA samples, sometimes also with samples that you get from the clinic that come from FFPE, that can also really drastically reduce some assays' performance. But if I have an assay that works nice in the sample type I want to use it on, generally I would say, well, that's robust for your application. Doesn't mean that not every assay needs to work well in a very crude sample, but if I work with very crude samples, I might have more requirements for my assay performance, and I might need an assay that is, generally speaking, a little bit less inhibited.
Yeah, I mean, it's also important to note. I mean, of course, we are aware of this, that digital PCR is generally not dependent on PCR efficiency. So even if you use crude samples with your assay and your assay is not working perfectly, usually that's fine as long as your positive cluster is separable from the negative cluster, which is a huge advantage of digital PCR.
Yeah, I think there's also one point. I've had some people ask me, "Oh, I've run this now, and my positive control has a higher signal than my crude samples." And I'm like, "Yeah, that's kind of makes sense." Also, the background, which is another part of this question, can also fluctuate. If I have a crude sample, potentially I have more background fluorescence, which might mean that if I end up with the same amount of signal from my assay, if my background is higher, it might not be as easily distinguishable. Then in the end, like you said, it's digital PCR. As long as I can draw my little threshold line between the positives and negatives, so go beyond the threshold, so to say, as long as that works, I'm still fine. And then it doesn't really matter. So it's not a problem if my signal is a little bit lower in some samples or the background is higher. As long as I can tell positive and negative partitions apart, that's all I need to be in the clear.
Cool. Let's see. What else have we got? What's the meaning of a single partition on the positive side of the threshold that can also be found in NTC? So in other words, what does it mean when in my NTCs I have a single positive partition, or some positive partitions for that matter?
I can tell you, if I pipette that, usually that means that I screwed up my pipetting, which is because I only work, I don't know, I work in a lab maybe every second month for a day or two. So I think that gives me a little bit of leeway. Generally, it is most often some contamination, which, to be honest, because dPCR is so sensitive, it's very easy to get a low amount of molecules, and it's very easy to get contamination, specifically if I work with positive controls.
If those are controls that are frequently being used in the lab, or if you're, I mean, I'm really sorry to say this, when a lab switches from qPCR to dPCR. Yeah, I saw some instances where out of a sudden dPCR, all the negative controls and all the NTCs were always positive for the target. And then unfortunately, you usually have to go and tell people that it's probably because your whole lab is contaminated with your positive control that you have been using for the past 15 years. And now digital, which is super sensitive, will pick it up.
Yeah, and it's often the case if they're like, oh, I normally everything above 33 in the qPCR, I just count as negative. That is a very good indication that you're not actually looking at negative samples, because even in qPCR, if everything runs perfectly, a single molecule should pop up at around 36, 37-ish, meaning that if your negatives have signal before that, there's probably something in there or something that is being amplified. Doesn't necessarily have to be contamination, can also be your sample or some off target, but it's a good indication that it's probably not quite as clean.
If somebody thinks, well, it might be contamination, what would be your recommendation to do?
Depends how you work, really. One of the things that I generally recommend is if you're working with a positive control, specifically if it's a synthetic one or a plasmid, their concentration is usually insanely high. It's just a lot of the same. And if you pipette that at the same place where you're pipetting your dPCR, you will never be happy. That is just the way it is. You will never have a nice NTC. It just doesn't work that way. It's too easy to get aerosol contamination in your plate. Yeah. So spatially separating that, only working with a very dilute positive control when you're pipetting it on your plate is one thing. Potentially spreading also the places where you do your pipetting, the pre and the post PCR, which is, a lot of people do that, which is very reasonable to do. And that way it's also easier to keep it clean. If you really have a major contamination in your lab, there's different things you can do. There are some filters that filter the air in the lab, but they usually take quite a lot of time before they really get all the amplicons out.
Doing my PhD, fortunately in a neighbor lab, and they removed everything. They cleaned the lab completely. They painted everything a few times. If you're not sure if you have contamination, I think the first step would be go another lab and pipette there. Yeah. I mean, of course, go in a lab where the positive control hasn't been used before. Pipette your PCR there. Go back and see if the negatives remain negatives, and that's a good indication for if you have contamination. Another thing you could do is switch positive control if you can. Use another amplicon. Use another positive control. Yep. And make sure to work cleanly the next time. And to going back to the question, I think one other point I want to make: if it's not a contamination, if it's a real NTC popping up, that usually means that your assay isn't clean, so that your assay is producing by itself for some reason, just generating a positive signal. There are two things you can do. You could redesign and try again, try a different sequence. Maybe just change primers first and see if they work with the probe, and see if they remain negative. That's the first thing you could do. And then the next thing you can do, if you have to keep that, run more replicates. See how many, do 48 NTC replicates, see how many positive partitions you get, and then you can calculate let's say, background positivity coming from your assay. And this value you have then to subtract from the value from the copies you actually get from your actual sample. So if your assay produces 2 positive partitions in 48 replicates, then you always have to subtract 2 from your actual sample.
Yeah, it's a so-called limit of blank, and if it's suitably low, it doesn't really matter too much, because if I have 15 times that in my positive samples, yes, it's not ideal, but it's only really relevant if you have samples that are really, really low concentrated. So you're really, really scraping the barrel, and you're only looking for 2 or 3 positive partitions. And then when your NTCs are not clean, then you have to subtract 2 of those, and then you end up with 1. So if you're going for ultra sensitive detection, or you want to look for an ultra rare target, make sure that the assay you're using is absolutely clean in your NTCs. Yeah, that's the recommendation. Well, yeah, and I think those are all the questions. Thanks for listening. Thanks for being here and answering all those questions. And I'm looking forward to see you in 4 weeks' time. So see you again next time, and have a good one.
QIAGEN. Sample to insight.